In this session, we'll be exploring one of, if not the most, developed sensing technique in the world, and that is machine vision. Now, whether you want to take a photo and make sure that Snapchat filter makes you look extra good, or whether a driverless car is trying to navigate the environment, all of these applications require advanced sensing at a distance, which is where machine vision really excels. Now, there's a common misconception that images is vision. If I gave someone an image, it doesn't mean they can see what I want them to see in that set of data. Now, I know that is quite hard to comprehend because as humans, we are extremely good at picking patterns, especially from visual data. But when you go to digitalize that process, that's when things get quite tricky, and that's where you need to develop machine vision algorithms. So today should be a great session because machine vision is literally everywhere and it's such an interesting technology to look at. Joining me to explore machine vision with you in this session is Dr. Derek Long. Now, Derek is a friend of mine, but also a fellow researcher at the University of Southern Queensland. He is a specialist in machine vision and he's worked on countless projects to help farmers farm more efficiently using machine vision algorithms. That has included working with people like John Deere or putting vision sensors on drones, flying them over crops and analyzing those images in real time. There's some really cool projects that he's worked on, and it's great to have him in this session demonstrate machine vision live and show you exactly how you can develop your very own algorithm. So in this session, we're going to explore machine vision. We're going to learn how color is then digitalized and algorithms are created. And also we're going to allow you to design your very own ag tech algorithm to identify fruit, flowers, or weeds in your very own garden. So this is the biggest prize draw for the entire program so far. It is up to $600 of prizes we're giving away just for participating in today's activities. Thank you again to Diode Magazine and Core Electronics for contributing some of these prizes to our students. Now, the prizes include a 1-year Diode subscription, a microbit, which is a small programmable microcontroller, and 5 tickets to our brand new AgTech Machine Vision workshop. That workshop will be incredible. It'll be something that no one has ever done before. You'll actually be developing your very own machine vision algorithms with us. That'll be an extremely great prize to win, especially if you are interested in learning more about robotics and machine vision. Again, there are some major prizes, $2,100 worth of major prizes to give away. All of this information I'll summarize and present at the end of this video. Now, machine vision can be described as the ability of a computer to abstract high-level understanding or extract information from digital images or videos. It is not the camera or the hardware providing these images, it is the algorithms or the software interpreting them. Now, I've got a crash course video here that does quite a good job of describing and introducing machine vision.
Hi, I'm Carrie Ann and welcome to Crash Course Computer Science. Today, let's start by thinking about how important vision can be. Most people rely on it to prepare food, walk around obstacles, read street signs, watch videos like this, and do hundreds of other tasks. Vision is the highest bandwidth sense, and it provides a fire hose of information about the state of the world and how to act on it. For this reason, computer scientists have been trying to give computers vision for half a century, birthing the subfield of computer vision. Its goal is to give computers the ability to extract high-level understanding from digital images and videos. And as everyone with a digital camera or smartphone knows, computers are already really good at capturing photos with incredible fidelity and detail, much better than humans in fact. But as computer vision professor Fei-Fei Li recently said, just like to hear is not the same as to listen, to take pictures is not the same as to see.
So when we talk about extracting key information or understanding from images, what are we really talking about? Well, there's different things that we can extract from images, and they depend on what algorithm types we want to use. For example, we might want to classify images. If we look at an image, we might want to say, this is image A or B type. This is an image of a cat or a dog. We also might want to detect objects or even track them. Now, that's basically saying that if I have an image here and I can find an object in that image, where is it in the next image? And where is it in the next image? And as we do that, we are tracking that object in a video. We also might want to use segmentation. That is essentially when you look at an image and you can define what is related to what. For example, if you've got a car traveling along and you've got a person and you found both of these objects in the image, and when they come close together, maybe the machine vision algorithm has to determine which is which and put a boundary around them so they know which part of the image belongs to each thing. Lastly, you can use machine vision to recreate or reconstruct images based on what it knows it should be looking for or seeing in the image. Now, these are just a few different functionalities of machine vision. There are so many different types. So now we know about machine vision, let's actually build our very own object detection algorithm. Now, if you remember, we have to tell the computer what to find and how to find it. And essentially that is our algorithm. Now, what to find could be looking for red pixels, and we'd tell the computer to apply a color filter to do so. Otherwise, we could look for a change in brightness in nearby pixels, which is an edge filter, or we could tell it to find formation of similar pixels, which is a shape filter. Now, I want to use the example of Where's Wally because that's something a lot of people can relate to. He's extremely hard to find in the images that you look for him in. Now, to do this, we are going to build a machine vision algorithm to find him in those images using the color and the shape filters. Now, this is the raw data. This is the image. You can see it is very crowded with irrelevant data, and that's the art of applying filters to simplify all this data and draw information from the image rather than just try and look at all this data that's irrelevant. So before I apply a color filter to that image, let's just take a step back and look at what is color and how do we digitalize it. So for computers, color isn't a name. It isn't red, blue, or green, or purple, or pink. It is a numerical proportion of red, green, and blue. So RGB is the default method of digitalizing color, as well as is the method that color can be digitalized on a screen. So you can see this cube just here, and we've got an amount of red, amount of green, and amount of blue. Now, the reason why we can go from 0 to 255 is because that 255 symbolizes a byte of data. Now, there's a lot of things that I could go into about digital electronics, but just know that in any color we choose, it's going to be between 0 and 255 for red, green, or blue. So if I wanted to give you an example, for example, we have indigo. Indigo, sitting just down here, has a lot of red, if we look at this axis, a little bit of green, if we go vertically, and a lot of blue. And so indigo could look like 255, 30, and 240 if you describe it as an RGB value. Now, have a go at aqua. See if you can try and describe what would aqua be. Does it have a little or a lot of red? Does it have a little or a lot of green? Does it have a little or a lot of blue? So we have these values here that correspond to aqua. Aqua is our human label for a color, but if we want to describe it to the computer and we say, filter this image and only find aqua pixels, we would need to give it these numbers here. So let's apply our color filter to the Where's Wally problem. So we know Wally is red, and I've applied this filter with a red that is actually 204, 18, and 4 in an RGB format. And this is what we've found. Now, to us, it doesn't look like it's very helpful, but to a computer, it is extremely helpful. See, what we've told the computer is, don't worry about looking at any of the pixels that are black. Only the white are the things that we need to care about. And that has dramatically reduced the amount of effort and time that the vision algorithm has to look at the image. Now, if I flick back, you can see that there are in fact parts that have red that are white. Now we're going to apply another filter to make it even easier to find Wally, but I can guarantee you that Wally is in one of these white dots. Already we know that, and it's already made it easier. So let's now apply the shape filter. Now before we start, there are two types of shape filters. One is size and one is circularity. Talking about size is essentially the number of pixels in this shape. Now I've put some shapes here below, and I've put a checkered board behind this to symbolize how many pixels each of these shapes are. You can see that this one is 13, 14, 3, and 10. So if I want to apply a filter to get rid of the smaller shapes, for example, get rid of anything that isn't more than 11 pixels, you'll see that we can omit some of those shapes. Now that might be useful, for example, of clearing small speckles like we have currently. We might then apply another filter or extend this filter and say we want to make sure that we filter anything below 11 pixels we get rid of, and anything 14 above we get rid of as well. And by applying that filter, we get this circle here that has 13 pixels. So that is one form of a shape filter. Now, we might want to use circularity. Circularity describes how circular is the shape that we're looking at now. And it isn't a number, but it's actually a ratio between 0 being absolutely not circular and 1 being the perfect circle. So again, we'll get these shapes back again, but now we've actually graded how circular they are. Now, there's a lot of mathematical equations that happen behind these algorithms. I'm not going to talk about that particularly, but just know that this is approximately their circularity, 1, 0.2, 1, and 0.8. So again, we can apply another filter here and say that we want to filter it so that we get something that is not a circle, which means we're filtering to keep something less than 1. And you can see obviously the perfect circles we had are disappeared now. We might then apply another of these filters and say, but we want something that's actually quite circular. So really we're looking for something that is more than 0.5 but less than 1. And you can see that our rectangle now disappears and we are left with our pentagon. So if we know what type of shape we're looking for, we can apply the filter and just get that from the image. Now back to our example with Wally. We know that we've applied our color filter and we've got Wally somewhere in here. Now, we want to get rid of all these little pixels that were the color red, but really aren't as significant to say that Wally would be them. I mean, the author would be quite sadistic if he had Wally in one of these dots. So let's actually apply a shape filter. And you'll see we're left with that dot and that dot here. Now this is applying the size, keeping anything that is above 10 pixels. So all those small pixels that really didn't matter, we've gotten rid of. And already at this point, we know our vision algorithm has determined that Wally is either that one there or that one there. Now, if we know Wally is a certain size, we can apply another size filter. For example, reduce it so that we only find pixels that are between 10 and 20. Then we know that this must be our Where's Wally. Now for the final reveal, let's see if our machine vision did work. So you can probably see that our vision algorithm has really helped to find Wally. And if you can't see Wally now, maybe you should check your eyesight. So comparing a raw data such as this image here and our machine vision algorithm here, you can see that it is incredibly easy now to find Wally if we overlay that on that. We've simply used a few filters such as color and a few size filters, and now we've found Wally. It is now my pleasure to introduce Dr. Derek Long from the University of Southern Queensland. He'll be showing us just how he develops machine vision algorithms for ag tech applications.
Hello everyone. My name is Dr. Derek Long. I'm a researcher at the University of Southern Queensland, and I'm here to talk to you today about my work in machine vision. My role and my job at the university is to take the machine vision, computers seeing technology, such as is entering self-driving cars, and help bring those into other aspects of our lives, specifically agriculture. There's a lot of things we can do with our new technologies that are coming into our smartphones, into our homes, and there's a lot we can do to help that, for it to help us grow food and fibre to help feed the world. And so that's what I do for a job, and I'm going to share that with you a bit today. I get to apply this across lots of different cameras and lots of different images so that rather than having someone have to look at them all, we can immediately have the computer read in a picture and show our results. And this can mean handling how water and how chemicals are used on our farms. If we can use those more efficiently, we can grow more food and fibre safer and better for our environment, and that's the core of what I do. I made my start with using drones and thermal cameras, using thermal images to see how water was travelling in an irrigation. So I got to make my start with thermal cameras, which was a lot of fun. And since then, I've got to go from drones to cameras that are on tractors and to cameras that are on our smartphones as well, and use those in different ways to look at looking at plants and looking at pests, so that we can really control and farm as best as we can. Today I've got 3 activities I'm going to take you through to understand some of the basics in what goes behind machine vision. We're going to look at the colour of some fruit and then the shape of the fruit, as well as some edge detection, and that can help show you how computers can see these objects. I've put some fruit out on a mat in front of us, which you can see on the screen. And to talk about colour, even as you're viewing this video now, the computer is telling the screen 3 pieces of information for every pixel on your screen. It's telling it how much red to show, how much blue to show, and how much green to show, RGB. And so that's how a computer breaks down colour. So the orange here might have a lot of red and not much green and not much blue. For the green one up here, lots of green and not much of the others. And yellow, of course, can be between red and green. So we could tell a computer to look for these colours. If I clicked on the orange here, it's now showing me all of the pixels that are kind of in that range of numbers. So everything else has gone away, which is black, and just that orange is showing up as white. So if I move it, pick it up and move it, you can see it follow. If I can do other things as well, such as tell it to close in, fill in the holes. So we're looking at, excuse me, one nice round object. And then I could also have it draw a circle around it too. So we've kind of just made a fruit detector, something that found all the orange pixels, grouped them together, and then drew a circle around each object that it saw. And that's the first exercise. The second one I was going to show you was shape. So if I start again and open up the webcam, I have 2 differently shaped yellow objects. I have the banana and what looks like in the shape of a pear. And so if I again go to look at the yellowish pixels, and then I bring them in together, I could have it tell me how round each of those shapes is. So for example, there's 2 shape numbers up there now. It shows the size of each one, and the shape of the top one is very close to, it's like 80% round. You can see the 0.8 there, and the banana is only 0.3, which is a very, very different, showing the different shapes. So I could have it search for only banana-like objects. So if I told it to only show me things that are 30% or lower, what do I get? I get just the banana. So it's not really showing the pear, but even though they're the same color, I'm now tracking only the banana. So as I said, starting with yellow pixels, then bringing them together, and then looking for different shapes. I've changed out the fruit now for some grass, and I'm going to use this to show you how objects of the same colour can still be distinguished, like grass and some leaves on top of it. This has application when we're looking for weeds out in the field. If a tractor's driving along that has a camera and it needs to see only where the weeds are and not, say, another plant so that it can spray it, it is just looking all at green plants, so it needs to use different information to tell between the two. And so edges are one way to do that. The grass here is very rough, but these larger leaves are smoother, and so we'll be able to tell them apart that way. And I'll show you now. I'm going to start by entering in the numbers that kind of represent green, so that we can take away the rest of the background. So now we've kind of got the green grass and those leaves there. I'm going to fill in the holes again so that we've got one nice good patch of green. And so now I have everything that's green. So I've removed just some of the corners of the picture. And now I'm going to bring up those edges. So now I'm going to start again. Now have a look at these edges. You can see that the grass is very, very busy, but there's no edges in those larger leaves. So this is something I can use to tell the leaves apart. I'm going to close it in again. Now I have a big hole where these leaves are. So I'm going to change it so that the leaves are white. Now, there's still some other stuff on the frame. It's not just the leaves there. So that's where I can come back and use the color to help me. I'm going to close up again. If I combine the two, so I go back to my big blob of color, which is taking up most of the screen, and then I look at the areas that are flat, and I tell it to show me only both green things that don't have a lot of edges, I then get this, which is basically just the leaves. So if I move them around, if I pick them up and move them, it's only really the leaves there that are now on the screen. And we could draw a square, a target around those as well. So that's another way that we can use relationships between pixels or different colors or small changes in texture to tell things apart. Some of these are the basic building blocks that go behind how machines can sort, say, bottle caps of different colors or find many objects, and it builds into things like detecting a person, detecting a face, having facial recognition that might even be on a phone or a computer that you know. These kinds of machine vision technologies are starting to be everywhere. You'll encounter them a lot as you finish. As you enter the world, it'll be a big part of engineering and a big part of IT in the future. And so it's important to have an understanding of how these are. So thank you for listening to an introduction into how machine vision works. I find it very interesting, and I really love bringing it to our farms so that we can have all of the great benefits of technology there on our farms as well. Anyway, that concludes this workshop. Thank you for listening.
So for today's activity, we will be designing our very own machine vision algorithm for your backyard. It should be a lot of fun. Now, to get started, you'll need a pencil, an eraser, access to maybe your parents' mobile phone or something you can take a photo with. That might be the webcam of your laptop. It could be whatever. And probably most importantly for this day, a template to use. Now, if you haven't been on our website, please feel free to go there and download this template so that you can use it for this activity. If you can't or you don't want to and you've got a blank A4 piece of paper, feel free to use that and just pause this video and write down the headings you see here as well as the table that you see here. It will be very useful for you for this session. So let's get started. We're going to do this in 2 steps. The first step is you're going to go exploring around your garden and taking photos of what you want to develop your algorithm to do, whether it's find a fruit or find a flower or even find a weed. You can be completely creative with this one, and it'll be a lot of fun to see what you guys come up with. The second stage is we're going to come back and we're going to develop our algorithm and draft it right here. So I'll show you my examples of things I found in the garden that I might want to develop an algorithm for. Then I want you guys to go and get your own, and then we'll start doing this together. Now, I went through the garden and I found a few different types And so one of the types I found was this one. I found some berries hanging on a bush. I do want to caution everyone, do not eat any berries you find in the garden. That is not a good idea. So make sure you're taking photos but not touching too much else. I also went through and I found some flowers that were really nice. And I found a mandarin on one of my mandarin trees. Now, a big hint for you guys to take photos of this stuff yourself. Try and take photos of whatever you want to find in most of the image. You can see the flowers take up most of the image. The mandarin is quite close to the camera. And also the berries I took have a really nice view of the camera. Now, also, you want to capture the natural environment. So do your best to take whatever you're trying to do your algorithm to identify with a natural environment, such as leaves that it's sitting in, like you can see in this photo, or the bush that the flowers are growing out of. You can see I'm kind of taking a photo from top down, so I get the background to be mostly green and uniform. You don't want to have random things in the background because that makes your algorithm less effective because it's got more data and more different colors and more shapes and a lot of different things that it needs to account for that aren't kind of usual in the environment of whatever you're trying to detect. So make sure you take the photo in that regard. So please feel free to pause the video now and go explore and take some photos. And when you come back, we'll start to the next stage. Cool, so we're back and we're going to develop our algorithm to detect, and I'm going to do one on this mandarin. I particularly want to find a mandarin in this bush. So, first thing I'm going to do is I've got to fill out these details. So I'm just going to quickly write my name, my grade, and the postcode. So that's done now. And the design title, because I'm finding a mandarin, I might call it Project Fruit Finder. Now, obviously everyone should know that depending on the photos that you've taken will depend on all of the answers we're going to put in here. So I want to make sure to note that this is all an approximate draft of an algorithm, and this is a really great way to start making your algorithm. But it is approximate, so don't feel like you have to get everything 100% correct. And obviously your answers, depending on your photo, might be completely different to my answers. So I'm going to try and walk you through so you can do it for your own photo. Now, the first thing we're looking at is we want to find color, shape, and edge of the thing we want to find, whether that's a flower or crop or whatever you've taken a photo of. And we want to also know what not to find, such as what do the weeds and backgrounds generally look like, and what colors, shapes, and edges are they? Now, these are filters we've looked at today, and so we're going to go through it and develop it based on what we've learned today. So we're going to start with color. Now, I'm going to just quickly show my image here. So if you look at my image, the color difference between what I want to find, the mandarin, and the background is obviously quite dramatic. So the color filter is going to be really effective for me to use in my algorithm. If yours are kind of the same color as your background, that's when you might have to be a little bit more tricky and think about edge and shape. But mine, color, is actually really obvious. So I'm going to write down in my algorithm draft that the thing I'm trying to find, which is a mandarin, is actually bright orange. Now, for those that just want to keep it simple, feel free to keep that answer there. But for those that want to challenge themselves, feel free to convert that color into a digital form. And by that, I mean, try and describe the red, green, blue value of this color. Now, you can guess, or you can go to a website, and there's tons of websites online that can help you determine this. So one example here is I've got this website open, and I've just Googled RGB conversion, and obviously this one here is rapidtables.com, so feel free to go to this one, use it yourself. And if I go here and I scroll down and I find the color that is most like the mandarin, which I'd say is probably that one, I can actually see the red, green value and blue value of that. So I'm going to write red as 255, green as 128, and blue as 0. Now, if you're guessing, just have a think. What would be the most likely, the most color in the color you're trying to find? Orange, I would have guessed it would have been almost all red because it's quite a bright and also hot color. And maybe a bit of green to make it from red to orange, and maybe not that much blue, otherwise it'd become a cool color again. So if you're artistically minded, have a bit of a brainstorm and try and guess, and maybe check what you find on these online websites. Otherwise, just jump straight to a website, or otherwise just give it your best guess. Again, this is just a draft. Now, the other colors that were in my picture in the background were brown and green. Now, I'm going to keep today's activity simple, and I'm just going to write the words brown and green. But you can see that I could actually put these types of browns and greens as RGB values here too. But I'm going to keep it simple, and I'm just going to write brown and green. And so the next one I have is shape. Now there's two types of shape filters we can do. We can do size and circularity. Now I'm just going to pick circularity because we've actually covered size in today's activity, and I want to give you a taste of how circularity would work. And also circularity would work really well in my application where the mandarin is actually quite circular. So if we look at what I'm trying to find, which is the mandarin, that is almost a perfect circle. I wouldn't say it is, but it's pretty close. Now, if you remember from today's session, 0 was not circular at all, and 1 was completely circular. I would probably guess the circularity is almost at 1, but not quite. So maybe I can write circularity as 0.95. So that's what I'm going to write here. Again, this is simply just a draft and just a way to understand what our algorithm might happen. And we could put in 0.95 and later adjust it and see what happens. Now, the background were leaves and tree trunks and tree branches. All of them were kind of straight and narrow, and the leaves may be partially circular, but not really. And so although I could estimate a circularity value for this one as well, I'm just going to write down not very circular. Now, if you want a challenge and you think you might be able to give it a go, feel free to estimate what you think the circularity is. And by doing that, all you have to imagine is drawing a circle around the object you're looking at and seeing if it would fill most of that circle. There's a lot of mathematical calculations behind machine vision that calculate this type of thing. But really, if you just think about circling it, if your object fills that circle and doesn't overlap too much, and it's near a perfect circle, that's when you can give it near a 1 value. If it's a long stick, it's not going to fill that circle at all. It's going to be near 0 value. So have a bit of a guess and have a bit of a play. Now, you can do size if you want to put size in here, but I'm going to skip that for now, just to make this activity a bit shorter. The last thing we're looking at is edge. Now, if we look back at my image, it looks like in the background here, there is a lot of scatter. There's a lot of edges happening, and it's mostly because things are overlapping each other and there's light coming down and there's so much happening in the background. There'd be a lot of edges happening. Now, looking at the mandarin, really that would just be almost one edge around the whole thing. I mean, maybe a few small edges because of that, that divot that you can see. It looks like bacteria, fungus, or maybe just some dirt sitting on the surface there. But overall, there would be very little edge. So I'm going to write here, and I'm not going to go into detail for edges because we didn't cover too much of it today. So I just want to generally describe it. I would say that there is very low edge activity. Now, obviously in the background, it's actually quite different. It's probably moderate to high edge activity. So this is the analysis, and by looking at the analysis, we can then start drafting what an algorithm should be. Now, in general, we want to look for what we're trying to find and not look for the thing we're trying to omit from our identification algorithm. So really, I'm going to write look for, and because I know the RGB, I'm going to put the RGB in, because this is for color, and it was 255, 128, and 0. But not look for brown or green. Now for a challenge, as I mentioned, you could put the RGB values in for that, for your own image. The next one is look for a high circularity. This might mean maybe we look for above, maybe 0.9. If our Mandarin was 0.95, we could say above 0.9 would find basically all the Mandarins we could find. And with this stuff, there's always exceptions, but we're just writing a general algorithm that would work most of the time. To get an algorithm to work all the time is sometimes near impossible, especially in agricultural applications. So we've got high circularity we were looking for, but not looking for a low circularity value. Now, because we're looking for above 0.9, maybe we could say anything below 0.9 is not really what we want to find. And lastly, we're just putting in for the edge activity. So the Mandarin for me we want to look for a very low edge activity, but not a moderate to high edge activity. Now, this is essentially our plan for developing a machine vision algorithm to find my particular application of a Mandarin. Now, yours might look completely different because your photo or whatever you're trying to detect and what the background is completely different. So that's okay. Hopefully you can follow along and just follow the steps that I've done to be doing your exact application. Now, today's activity, you'll need to submit 2 photos. The very first photo you need to send is the photo that you want to analyze. The second photo you want to send is a photo of your worksheet here. So essentially it should be a photo and the other photo of the actual garden, whatever you're using. So best of luck. I'm really looking forward to seeing what you can create. Now onto the prize giveaway. Now, before I start this, I just want to say a huge thank you to Diode and Core Electronics for being the major sponsors of this event and giving us such awesome prizes to give away. Now, the prizes are on offer are just listed above me, and we're going to pick 5 random people from all the people who submit for today's activities, and this will happen each day. Now, of those 5 winners, the very first drawn student will get one of everything listed here. The 4 other winners will get one of this prize here for the 4 remaining prizes of this one. Now, how do you submit? Well, it's quite simple. The first thing is follow along with today's activities and take a photo of your work. Make sure in that photo you have the details such as your name, your grade, and your postcode so we can see who's actually submitting their design for this competition. Step 2 is to share that photo with us. The easiest way to do that would be to post it in the Facebook comments below this video. Or if you want to email it to us, feel free to do so. Our email address is info@integratedSTEM.com.au. If you are emailing it to us, please be sure to use the heading of the session. Now, the heading of the session is above on this slide at the very top. So just use that in the subject box of your email. Lastly, be sure that you have liked our Facebook page so that you can see the announcement of the winners. Now, if you need to find our Facebook page, you can search us using the @integratedSTEM.com.au on Facebook, and you should find us. Very lastly, be sure that you get your entries in before they close. The closing dates are here now, and then the winners will be announced the following day at 5 p.m. For the major prize giveaway, you could win over $2,100 worth of prizes. For yourself, you could win a DJI drone, as well as a 2-week 3D printing program with us. And you could win exclusively for your school, our Machine Vision Ag Tech workshop. Now, registrations do close on August 28 at 1 p.m. and the winner will be drawn on the same day at 5 p.m. So to register, simply go to this website link here. It'll probably take you less than a minute to do so. On the website, there's 2 ways you can submit your entry. All the details are on the website. If you do both, you double your chances and you get 2 entries. Although this session was a little bit more technical, I do hope you enjoyed exploring machine vision, learning how color can be digitalized, and also developing your very own machine vision code. If you did enjoy this session, may I please ask you to share it on Facebook or just let other parents know that this does exist to help us inspire more kids in tech. We have tons of programs on our website that are to do with robotics and machine vision. Particularly, we've got a brand new machine vision course that we are developing now and delivering Australia-wide to give a completely unique experience to kids who want to actually develop their own machine vision codes. So please check that out. It will be an incredible opportunity for any kid that's interested in this technology. Otherwise, a huge thank you for tuning in, and we'll see you in the next one.